Welcome to Physics Lesson P003. Today we are going to talk about something you experience every single day: acceleration. Whether you are pressing the gas pedal in a car, dropping your phone by accident, or watching a cricket ball fly through the air, acceleration is at the heart of all of it. By the end of this lesson, you will understand exactly what acceleration means mathematically, how to read motion graphs with confidence, and how to break down projectile motion into something surprisingly simple. This topic comes up in almost every NET paper, so pay close attention. Let us get started. Here is something that surprised the whole world when it was demonstrated live on the moon in 1971. An astronaut stood on the lunar surface holding a feather in one hand and a geology hammer in the other. He dropped both simultaneously. They hit the ground together. On Earth, air resistance gives the feather a fighting chance. But in vacuum, both objects experience the same gravitational acceleration. This is the power of understanding acceleration precisely. It is not about how heavy something is, it is about the force acting on it divided by its mass. Today we will make this crystal clear with graphs, formulas, and worked examples. Acceleration is defined as the rate of change of velocity. In simple terms, how quickly is your speed changing? The formula is A equals delta V divided by t, which means final velocity minus initial velocity, all divided by time. The unit is meters per second squared. Notice that acceleration is a vector, it has both magnitude and direction. When you brake your car, you are still accelerating, just in the opposite direction to your motion. That is called deceleration. Free fall is the most important special case. Near Earth's surface, all objects accelerate downward at approximately 9.8 meters per second squared, which we round to 10 for NET calculations. Memorize this value, you will use it constantly. Motion graphs are a favorite in NET because they pack a lot of information into a simple picture. On a position time graph, the slope at any point tells you the velocity. A flat horizontal line means the object is not moving. A straight diagonal line means constant velocity. A curve means the velocity is changing, which means acceleration is present. On a velocity time graph, the slope tells you the acceleration. The area under the curve, the shaded region between the line and the time axis, gives you the displacement. This is enormously useful for solving problems without equations. Practice sketching these graphs for different scenarios: uniform motion, uniform acceleration, deceleration, and free fall. They come up repeatedly in exam papers. Projectile motion looks complicated but becomes simple once you understand one powerful idea: horizontal and vertical motions are completely independent of each other. The horizontal component moves at constant velocity, there is no horizontal force, so no horizontal acceleration, assuming we ignore air resistance. The vertical component behaves exactly like an object thrown straight up or dropped, it experiences constant downward acceleration due to gravity. So you split the initial velocity into its horizontal and vertical components using trigonometry, then solve two separate one-dimensional problems. In our example, a ball thrown at 20 meters per second at 30 degrees reaches a maximum height of 5 meters after 1 second. At maximum height, vertical velocity is 0. The horizontal velocity remains 17.3 meters per second throughout the entire flight. These four equations of motion are the foundation of all kinematics problems. They only apply when acceleration is constant and uniform, which covers most NET scenarios. The first equation gives you final velocity after time t. The second gives displacement. The third is incredibly useful when you do not know time but know velocities and displacement. The fourth uses average velocity as a shortcut. For free fall, simply substitute g for a and remember that downward is positive in most problems. The range formula for projectile motion, u squared times sine of 2 theta, divided by g, shows beautifully that maximum range occurs at 45 degrees, because sine of 90 degrees equals 1, which is the maximum. Memorize all four equations of motion, you need them in every physics section of NET. Let me give you the NET-specific strategy for this topic. Projectile motion and velocity time graph interpretation are among the most frequently tested concepts in NET physics. Expect 3 to 4 questions in any given paper. The golden rule for projectile problems is always split first, write down horizontal component and vertical component separately before doing any calculations. Never try to solve it as one motion. The time of flight formula, 2u sine theta over g, is a direct substitution question. Similarly, range is maximum at exactly 45 degrees. For velocity time graphs, always remember that the area under the curve gives displacement, and the sign of that area matters. Area below the time axis is negative displacement. These are the exact points where students lose marks. Let us wrap up lesson P003 with the 5 things you must walk away knowing. 1. Acceleration is the rate of change of velocity, measured in meters per second squared. 2. On a position time graph, slope equals velocity. On a velocity time graph, slope equals acceleration and area equals displacement. 3. The 4 equations of motion are your toolkit, but they only work for constant acceleration. For projectile motion is solved by splitting into horizontal and vertical components. Never try to handle it as a single motion. 5. Maximum range in projectile motion happens at 45 degrees. In our next lesson, P004, we move to Newton's laws, the rules that explain why objects accelerate in the first place. See you there.